Good morning, all of you. In today's class, we are going to discuss about the static electric field. Under that, the first topic is Coulomb's force law. The Coulomb's force law provides us the amount of attraction or repulsion that exists between two particles having charges Q1 and Q2. According to this Coulomb's law, the force of attraction or repulsion that exists between two particles is proportional to the product of the charges and inversely proportional to square of the distance. For example, let us consider 2-point charges Q1 and Q2. Q1 is placed at point 1, Q2 is placed at point 2. The vectorial distance between 1 and 2 is R12. Assume that Q1 and Q2 both are positive charges. Then Q1 will try to repel Q2 in its direction and Q2 will try to repel Q1 in the opposite direction. Let F2 is the force on Q2 due to Q1. Then F2 is equal to, or F2 is proportional to product of the charges Q1 into Q2 and inversely proportional to square of the distance. So inversely proportional to R12 square. So if K is the constant of proportionality, F2 is equal to K into Q1 Q2 by R12 square. The constant of proportionality is measured as 1 by 4 pi epsilon naught, where epsilon naught is permittivity of a free space. Its value is 8.54 into 10 to the power minus 12 farads per meter, which is also equal to 1 by 36 pi into 10 to the power minus 9. The direction of F2 is along the line 1 to 2. That means if I can define a unit vector AR12, then that is the direction of the force. So AR12 is equal to vector R12 divided by its magnitude. So the final expression is F2 is equal to Q1 Q2 by 4 pi epsilon naught R12 square. This is the magnitude of the force and the direction is AR12, unit vector along the line 1 to 2. For example, let us consider this problem. 2 millicoulombs of positive charge is located at point 1, 3 minus 2 minus 4 are the coordinates, and 5 microcoulombs of negative charge is at P2, 1 minus 4, 2. Find the vector force on the negative charge. So the vector force on Q2 is equal to Q1 Q2 by 4 pi epsilon naught R12 square AR12. So this 2 millicoulombs of point charge is at P1 minus 5 microcoulombs is at P2. The distance between P1 to P2 is represented by a vector R12. So vector R12, if you know the coordinates x1, y1, z1 of point P1 and let us say x2, y2, z2, the coordinates of P2, then R12 is equal to x2 minus x1 ax plus y2 minus y1 ay plus z2 minus z1 az. So 1 minus 3 ax, that is minus 2ax, minus 4 plus 2 ay, 2 minus of minus 4, so plus 4 az. So it is going to be minus 2ax minus 2ay plus 6az. What is the magnitude? Root of minus 2 whole square plus minus 2 whole square plus 6 square. So it is going to be root 44. So as it is, if you substitute in this expression, Q1, that is 2 into 10 to the power minus 3 into Q2 minus 5 microcoulombs minus 5 into 10 to the power minus 6 by 4 pi epsilon naught R12 square So root 44 whole square AR12, that is vector R12 divided by its magnitude. So finally we get this as 0.616AX plus 0.616AY minus 1.5 AZ. Now let us consider this problem. It is required to hold four equal point charges plus q coulombs each in equilibrium condition at the corners of a square. Find the point charge which will do this if placed at the center of the square. So let us consider a square. Because the side is not given, assume that the side of the square is A units. So these are the four corners 1, 2, 3 and 4. At each of these corners there is a point charge of q coulombs. So here at corner 1, corner 2, corner 3 and corner 4 there is a point charge of q coulombs. If we want these 4 point charges to be in equilibrium condition, that means in state of rest, what is the point charge that I am supposed to place at the center? Now let us see, why do we need an additional charge to be placed at the center in order to have these 4 point charges in equilibrium condition. So for that, if you find out the force experienced by any charge, for example, let us consider the point charge placed at corner 1. The charge at corner 2 placed at corner 2 will try to repel this with a force of F12. What is F12? Q square by 4 pi epsilon naught. Distance is A. So 4 pi epsilon naught A square, and this is the direction of the force. Similarly, F14, the distance is same. So magnitude of F14 is same as magnitude of F12. Q square by 4 pi epsilon naught A square. But the directions are different. F12 is acting in this direction to the left hand side. F14 is acting in the downward direction. And because the magnitudes are same, what is the resultant of F12 and F14? Resultant of F12 and F14 will be in this direction, diagonal direction. And what about F13? F13, that is the force on Q which is placed at corner 1 by the charge placed at the corner 3. So this is the direction of F13. So direction of F13 and the resultant of F12 and F14 both will be in the diagonal direction. So ultimately the charge which is placed at corner 1 experiences a force in the diagonal direction. Because the situation is going to be same at the other corners, this also experiences a force in this direction, this experiences a force in this direction, and this experiences a force in this direction. So as it is, if I place 4 point charges at the four corners of a square, and if I release my hold on the 4 point charges, what happens? Each point charge will try to run away from the rest of the charges because each experiences a force in the diagonal direction. So each point charge will try to move away from the other charges until the force of attraction or repulsion becomes zero. But here the problem is, I want these 4 point charges to be placed at the four corners in equilibrium condition. So for this, what is the point charge that I am supposed to place at the center? Now just now we have seen that when I place these 4 point charges at the four corners, Each point charge experiences a force in the diagonal direction. So if I can create equal and opposite force, then these two forces will be nullifying each other. So if this is the repulsive force and this is the attractive force. So in order to create this attractive force, naturally I have to keep a negative charge at the center of the square. The magnitude of the negative charge q dash has to be selected in such a way that the amount of attractive force will be equal to the amount of repulsive force. Okay, now let us do this problem. F1 to F14 already we have discussed that. Q square by 4 pi epsilon naught A square. And F12 will be acting in this direction. F14 will be acting along this direction. Suppose if I define this direction as x-axis, this as y-axis, what is the direction of F12 minus AX? What is the direction of F14 minus AY? Next, what is the magnitude of F13? Q square by 4 pi epsilon naught. From here to here, the distance is root 2a. So root 2a whole square. Q square by 8 pi epsilon naught a square. Now the resultant of F12 and F14. F12 plus F14 will be equal to minus AAX minus AAY. So magnitude is equal to A into root 1 plus root 1. So root 2A. And what is the direction? The direction will be along the diagonal direction. Total repulsive force will be F12 plus F14 plus F13. Because F13 is acting diagonally, resultant of F14 and F12 also will be acting along the diagonal direction. I can add these two forces. So root 2 times A. What is A? Q square by 4 pi epsilon naught A square plus F13 Q square by 8 pi epsilon naught A square. So this is Q square by 4 pi epsilon naught A square. If I take it as a common factor, this is root 2 plus 1 by 2. Now, in order to counter this repulsive force, a negative charge has to be placed at the center. Let that negative charge is minus q dash. From that negative charge to corner 1, what is the distance? 1 by root 2 into a. So attractive force is equal to q into q dash by 4 pi epsilon naught. What is the distance? 1 by root 2a whole square. So equating these two forces, attractive force is equal to repulsive force. Ultimately, you get this q dash as 2 into root 2 plus 1 by 4 into q. That means 0.957 times q. Now, let us define electric field intensity. It is normally represented with the letter E and the unit is going to be volts per meter. Electric field intensity is a force on a unit positive charge. So, wherever you want to find out the electric field intensity, you place 1 coulomb of positive charge and find out how much force it experiences. Now, just now we have seen that suppose there are 2 point charges Q1 and Q2. What is the vector force on Q2? Q1 into Q2 by 4 pi epsilon naught R12 square AR12. So, if I want to find out what is the electric field intensity at point 2 because of the charge Q1, what all I have to do is I have to make this Q2 as 1 coulomb because electric field intensity is the force on a unit positive charge. Electric field intensity created by Q1 at point 2 is the force experienced by 1 coulomb of positive charge if placed at point 2. So that is Q1 into 1 by 4 pi epsilon naught R12 square AR12. Instead of 1 coulomb of positive charge, if there is a charge of Q2, how much force it experiences? Already we have this expression. Q1 into Q2 by 4 pi epsilon naught R12 square AR12. So when I compare these two, we can write F2 is equal to Q2 times E. In general, F is equal to Q times E because electric field intensity is the force on a unit positive charge. Instead of 1 coulomb of positive charge, if there is a charge of Q coulombs, how much force it experiences? Q times E. For example, determine the electric field intensity at 0, 3 and 4 due to a point charge of 0.5 microcoulombs placed at the origin. So at the origin, there is a charge of Q coulombs, and at point P, 0, 3, 4, what is electric field intensity? What is the expression for the electric field intensity? Q by 4 pi epsilon naught R square AR. What is R? The distance from the point charge to point P, where we are defining the electric field intensity. Now, if you write an expression for R, 3 minus 0 AY, because x coordinate is anyway 0, so 0 minus 0 AX, 3 minus 0 AY, and then 4 minus 0 AZ. So 3 AY plus 4 AZ. What is its magnitude? Root of 3 square plus 4 square, it is 5. So electric field intensity is Q, that is 0.5 into 10 to the power minus 6. 1 by 4 pi epsilon naught is 9 into 10 power 9 by R square, so 5 square. AR is equal to a vector R divided by its magnitude. So its value is 108 AY plus 144 AZ. So many volts per meter. And one of the important things is both force and electric field intensity are vector quantities and are linear quantities. Linear quantity means, for example, you have a charge Q1 placed at point 1 and there is a charge Q2 placed at point 2, and you are required to find out what is the total electric field intensity at point P. What all you have to do is you need to consider these 2 point charges independently. That means find out what is electric field intensity at point P. Call this as E1 because of the charge Q1. What is that E1? Q1 by 4 pi epsilon naught R1 square AR1. Similarly, find out what is electric field intensity at point P because of the charge Q2. Let that be E2. And what is the total electric field intensity? E1 plus E2. So you get the total electric field intensity. Throughout the static electric field, our intention is to determine the electric field intensity at a given point for a given charge distribution. So in fact, charge appears in 4 different forms. One is a point charge, and then the line charge, surface charge, and the volume charge. Now, ultimately, at a given point P, we need to find out the expression for the electric field intensity due to these charges, whether it is a point charge or a line charge, surface charge or the volume charge. Our intention is to determine the electric field intensity at a given point. So in the next class, we are going to discuss about the line charge, and we discuss how the electric field intensity can be obtained due to a line charge.